Hello again. This is video lecture 28.1. So we're starting chapter 28, which is all about a new kind of vector field for us called a magnetic field. Everybody's heard of magnetic fields, and now we're going to dive into studying the properties of this vector field called magnetic field. So we're kind of doing a transition from studying electric fields to studying this new kind of vector field called a magnetic field. And then a little bit later after that, we're going to show how electric and magnetic fields are actually linked together. But we start with Chapter 8, Section 1, magnetic fields and the definition of magnetic field. And the first thing to be aware of is the symbol that we use in physics for this vector field called the magnetic field. Now we use the symbol E, as you know, for the vector field known as an electric field, caused by merely the presence of electric charge around. That's what creates electric field throughout all of space. And then if you bring in a particle with its own charge, Q, you can get an electric force, Fe, from the electric field using the simple old formula Q times E. Electric fields exert electric forces on charges. That's what we have been doing, part of. And now we have a new kind of field called the magnetic field. Now you might think the symbol for that might be M, but historically that just turns out not to be the case. The symbol for magnetic field is capital B arrow. It's a vector field, so we have to draw the arrow on top. And the symbol is B. And that is so commonly used that you'll often hear physicists call it the B field, and electric field the E field. But we'll say magnetic field. So how do we know there's such a thing as magnetic field? We have to be able to see the consequences of it. And one of the ways we see consequences of it, we learn by experiment, and a lot of it happened accidentally over the course of history. If you have an electrically charged particle with some charge Q, and it is moving around in the vicinity of something that's creating a magnetic field, you can see that the trajectory get affected by the field. In other words, there can be a force. So what we're going to start studying is this new kind of force, magnetic force. It's caused by a magnetic field on an electrically charged particle. So here's the scenario. Something creates a magnetic field, B arrow. This chapter, I'm not worried about what's creating it. We will learn in the next chapter, and then the next chapter after that, ways you can create a magnetic field, B arrow. We're just going to say for now that we have a magnetic field. One of the ways you can create a magnetic field is with a device called an electromagnet. That's a magnetic field created by moving charges, i.e. electric current. Another way you can have a magnetic field is a permanent magnet, and that would be historically how people recognized magnetic fields, as they came across, quite accidentally, something called a permanent magnet. And that turns out to be the magnetic field created by the alignment of little tiny atomic magnetic dipole moments. We'll have to learn more about that as we go, but that's what's happening in a permanent magnet, like the kind you put on your refrigerator. All right, then here comes an empirical fact from experiment. You have some amount of electric charge Q on a particle, and that particle is moving through a region of space where there's a magnetic field B arrow, perhaps because you're near one of these things called a permanent magnet. Then you can find that the particle experiences a magnetic force. Notice how we're going to denote that magnetic force. F sub B. Now, if electric and magnetic fields are related, and the formula for an electric force, F electric is Q times E, you would be perfectly reasonable to think that the formula for this new kind of force, magnetic force, F sub B, would be the electric charge times the magnetic field B. But that turns out not to be correct. Okay? There's a different formula. And I want to start, although I have the formula here on the screen, I want to try to motivate it for you based on what we'll call experiments by running some simulations from Wiley Plus. And from these simulations, we'll try to piece together the behavior of the magnetic force, and we will discover that it is more complicated than the electric force, at least in the situations we're dealing with. And we're going to have to try to deduce what the formula is for that force. So let's go first to a simulation on Wiley Plus. And one of the things we're going to have to get used to with the magnetic force that we just were not required to deal with the electric force is that we're going to need all three dimensions of space. So if we think about axes, we're going to need x and y and z. We're going to need all three. And that makes the magnetic force a little more complicated, but that's just the way it is. Now in this animation, you'll see we have an x and a y and a z axis. And we have a particle. It's that red disk, which you can see it's initially at the origin. And it's sitting in a magnetic field, maybe because we are in a region near a permanent magnet. But we're just going to assume that throughout this region, the magnetic field B arrow points in the plus z direction. Everywhere. It's uniform. So you can see we've labeled it there. See how it's B arrow? Now that's the magnetic field at the location where the particle is. Particle has some electric charge Q. Right now we're assuming that charge is positive. All right. Now, we're just going to put that particle at the origin and let go so that its initial speed is 0. I'm going to run the animation and I want to see what behavior we get for our particle. Time is running. Okay, notice. Nothing. Nothing at all. Okay, let that sink in first. If that were a charged particle Q, positive charge, in an electric field in the plus z direction, and I put the particle at the origin and let go, what would it do? It would accelerate with a force, because of a force, in the direction of E. It would accelerate in the plus z direction. It would keep going faster and faster. Notice, I have a charged particle, positive charge Q, in a magnetic field in the z direction, and the particle is initially at rest. Nothing happens. In fact, the animation shows you what the magnitude of the magnetic force is, FB, as a ratio of the biggest maximum magnetic force we can get, and it's 0. There is no magnetic force in that case. So it seems that the particle needs to be moving, as we observe it here in our reference frame. So I'm now going to click and give it a non-zero speed. And that, whoops, I need to reset this. That's now represented by the red arrow labeled V. And notice by default in the animation that V is in the plus z direction, just like that magnetic field that the particle is immersed in, B. Okay? So the V, the velocity of the particle initially, and the magnetic field B that it's in are parallel. Now I'm going to run the animation and see what happens. Okay, now the particle is definitely moving, but if you look carefully, you'll see the particle is not speeding up, nor is it slowing down. In fact, it's moving at constant speed in a straight line. So in fact, it's moving at constant velocity. And sure enough, it shows that there's still no magnetic force. So I have to have a charged particle, and it has to be moving, but apparently it has to be moving, the direction in which it's moving matters. So with these other sliders labeled theta and phi, which are both angles in degrees, I can change the direction of the initial velocity. Let me slide the theta to 90 degrees. Now look at what happened. Now I see the red arrow is along plus x. That's the velocity. The magnetic field the particle is in is still along plus z. And now look up here. FB over F max equals 1. Now I have a magnetic force, and it's the biggest I can get. And that blue arrow shows it. FB arrow. In this case happens to be in negative y. But what's kind of more important to notice is that the FB arrow, the magnetic force, is perpendicular to both the initial velocity, V arrow, and the magnetic field, B arrow, right? It's perpendicular to both. Okay, I'm going to run the animation in this case, and I want to see what kind of motion I get for the particle. Let's see what we get. Wow, that's interesting. Yes, that's a circle. I get circular motion. In fact, I get uniform circular motion, where the magnetic force is always towards the center of the circle, and that's perpendicular to the velocity vector. And so the velocity vector changes in direction going around, but not in magnitude. So all that work we did last semester to study uniform circular motion, that's going to pay off, because that's going to happen here. Now, here's an interesting question. Let's change the sign of the charge. Okay? Equal amount of charge, but it'll be negative now. Let's see what happens. Ready? Aha! The direction of the magnetic force, the blue arrow, it reversed by 180 degrees. It's still at a maximum magnitude, but its direction is reversed. That's the direction of F magnetic for a positive charge, and that's the direction for a negative charge. So definitely the sign of the charge matters. Now what do we get when we run the animation? Now we get another circle, but now its center is on the other side of the x-axis. Okay, so, wow. The charge has to be moving. It has to be moving in a direction that's not parallel to the magnetic field. And the direction of the magnetic force you get depends upon the sign of the charge. Let me take it back to a positive charge. And now let me change that angle theta from 90 degrees between V and B when I get the biggest F magnetic. And now I change that angle. Notice the angle of the velocity vector is changing. But the direction of the magnetic force is not changing. See the blue arrow? Direction isn't changing. It's just getting shorter, isn't it? So the magnitude of F magnetic depends on that angle theta between V and B. But the direction is still, well, what you see. Let's get that angle theta down to 30 degrees. Almost there. Boom. Look at that. FB over F max. See the value on the screen? It's a half. The magnetic force is half of its maximum. And its maximum happens when the angle theta is 90. And its minimum happens when the angle theta is 0. So there's some simple function of theta here that's involved. When theta is 0, it's 0. When theta is 90, it's a maximum. When theta is 30 degrees, it's half its maximum. Think of a trig function. How about sine theta? Because sine of 0 is 0, sine of 90 is 1, and sine of 30 is 1/2. So the force actually depends on the sine of the angle between V and B. Okay? All right, now the last thing is let's change phi. What does phi do? Well, it changes the angle of the velocity in the xy plane relative to the x-axis. So it makes the velocity vector not just along x-axis. Let's run the animation and see what we get. Well, we still get a circle. It just is more complicated as to where the center of the circle is. Okay? All right. And now one more thing. Let's put the phi back to 0. And let's put the theta down to something smaller, around 45. Now the initial velocity has an x component and a z component. A component perpendicular to the magnetic field, that's the x component, and a component parallel to the magnetic field, that's the z component. Now what trajectory do we get? Here we go. Wow. Okay, that's an interesting trajectory. Let's make the angle a little bit closer to 90. Maybe you can see better what it's going to be when I do that. It's a combination of circular motion, perpendicular to B, and constant velocity motion parallel to B, and that trajectory is called a helix, and we will talk about that in a later section. Okay, so my point is that this is a rather complicated force, and it takes a lot of experimenting to get the formula for it that describes that force. I'm just now going to tell you the formula for it, and then we're going to talk about it. It's right there in the middle of the screen in the red box. The formula for calculating the magnetic force F sub B arrow on a charged particle moving in a magnetic field B arrow. You take the size of the charge Q times, and yes, that's a vector product or a cross product. Remember that from last semester? Velocity cross magnetic field, V cross B. That is the succinct mathematical formula that it turns out will be in agreement with all of the behavior we just saw in the animation. Q times V cross B. I'll say again, Q times V cross B. That's the formula that is the main formula for this chapter. And really, in some sense, the rest of this whole chapter is practicing at applying that. And it's complicated enough that it takes a good bit of practice. All right, first of all, let's talk about how to calculate the magnitude of this force. Then we'll worry about the direction. Magnitude. Notice how I denoted that. FB arrow absolute value, right? Magnitude. Well, this would be true for any cross product. If I give you any kind of formula, blob equals that, right? Where those can be absolutely anything. C arrow equals a scalar little a times B arrow cross D arrow. How would you find the magnitude of such a thing? Of C, this thing? Well, for any cross product, the magnitude is the magnitude of the first vector times the magnitude of the second vector times the sine of the angle between them when they're drawn with a common tail. And now we just have to carry along that scalar out front as well. And that scalar might be negative. So here's the formula for FB magnitude. Magnitude of Q, because Q could be negative. We don't want that. Magnitude of V, arrow, magnitude of B, arrow, sine theta, where theta is the angle between V arrow and B arrow when drawn with a common tail. So, on the previous animation, I had a magnetic field that pointed straight up in the plus Z direction. There's my particle, and one of the ways I had the V arrow was straight out along Z. So this is, along X. This is the X direction, not going this way. And then the Y was going that way. Okay? Then the theta is the angle between the V and the B when they're drawn with a common tail. Now that shows the theta being 90. It doesn't have to be 90. Okay? All right. So that's the formula for calculating the magnitude of the magnetic force. Notice because of the sine theta, if theta is 0, the force is 0. If theta is 90, the force is a maximum. Okay. Now what's the SI unit of magnetic field, the B? Well, look at the force formula. The quantity on the left, force, has to have the SI unit of Newton. Now on the right, the quantity of charge Q has the SI unit of Coulomb. Velocity magnitude has unit of meter per second. And units obey algebra just like symbols. So you can solve for the units of B. Remember, a Coulomb per second is an ampere. This combination is really ampere times meter. And so the unit of magnetic field, B, is 1 Newton over ampere times meter. And that combination, Newton over ampere times meter, that unit's given its own name. It's called the Tesla, capital T, named in honor of Nikola Tesla, who was a brilliant engineer in the 1800s. Okay, so I just said this, but let's see if we're paying attention. What angle theta between V arrow and B arrow gives the largest value of FB magnitude? Do you have the answer? Did you say theta must be 90 degrees, like my drawing? because it all depends on sine theta. 90 degrees gives you the largest sine. What angle theta between V and B gives the smallest FB magnitude? Did you say 0? Because the sine of 0 is 0. Or 180. The V and the B could be exactly opposite. That would also give you no magnetic force. All right, next. What is the direction of this force, FB? Well, again, it comes from properties of the vector product, the cross product. And we're going to need this thing called the right-hand rule from last semester. All right, so if you have a cross product of two vectors, in this case, velocity and magnetic field, V cross B, and you're using that along with multiplying by Q to get the magnetic force, what can you say about the direction of the magnetic force? Here are things you can say. F magnetic is perpendicular to the mathematical plane formed by V and B. Okay, let's apply that to our picture right over here. The magnetic field B and the velocity vector V lie in the xz plane in this picture. That's a mathematical plane, the xz plane. Then we know the magnetic force, since it comes from the vector product, V cross B, is perpendicular to that plane, which means it's perpendicular to both V and B. Since that plane in this case is the xz plane, you only have two possibilities for the direction of F magnetic. Plus y, that's perpendicular to the xz plane, or minus y, that's the minus y direction, which is also perpendicular to the xz plane. Okay? All right, so which of those directions is the correct one? Well, we need the right-hand rule. First, we use the right-hand rule to find the direction of V cross B, just that. Okay? And we're going to review the right-hand rule, and I tend to use like two pens. So in this case, since we're drawing the velocity vector as red, I'll use a red pen for the velocity vector, and the magnetic field is green, so I'll use a green pen for that. And I put the green one in the direction of B, and the red one in the direction of V, okay? And I do V cross B. I hold them together with my left hand, and this is going to look perhaps reversed to you, but I am holding them in my left hand with B up and V in what would be what we're going to call the plus X. And then I reach in with the fingers of my right hand, thumb outstretched like I'm hitchhiking, and I push V on top of B in the shortest possible direction, which would be this way. And I see which way the thumb points. And that direction of my outstretched thumb is the direction of V cross B from the right-hand rule. We're going to practice with that. But then there's a couple more steps. Well, there's really one more step. If the charge of the particle is positive, then I'm multiplying V cross B with a positive scalar, the Q, and so the direction of F magnetic is the same direction as V cross B, parallel. But if the particle's charge is negative, Q is a negative number, then in the formula for the magnetic force, the Q there times the V cross B, the Q is a negative scalar. That means the F magnetic is exactly anti-parallel to the direction of V cross B. Okay? All right, so for the picture I've drawn, the right-hand rule tells me that the V cross B is in the negative y direction. And then the direction of the force all depends on whether that particle's Q is positive or negative. If that particle's Q is positive, then F magnetic is the same direction as V cross B. And if that particle's Q is negative, then the F magnetic is exactly opposite to V cross B. So, if the particle's charge is positive, F magnetic is parallel to V cross B. If the particle's charge is negative, F magnetic is exactly opposite to V cross B. Let's actually do a little bit more drawing of pictures for this right-hand rule. Visualizing the right-hand rule in the magnetic force law. So what we've got here is a picture showing a particle. Apparently it's moving around on a kind of a tabletop, and it's got a velocity vector at a certain instant in time. I'm going to draw it in red. And it's at a location where there's a certain magnetic field this way. I'm going to draw it in green. And they both those arrows are lying on that tabletop, on top of the table. Okay? So for my table, I've actually, you can't see it, but I've actually got a red pen and a green pen, and they're resting on a tabletop. Okay? And the V is kind of pointing away from me, and the B is pointing a little bit closer to me. And then I need to take my right hand with my thumb outstretched like I'm hitchhiking, and I reach in so that my palm is along V and facing B. And then I can curl with the fingers of my right hand the V on top of the B. Always do V on top of B, and I see which way my thumb points. And that's exactly what this diagram right here is showing. See how your thumb is pointing and your palm of your right hand is pointing, and your fingertips of your right hand are ready to push V on top of B. And here, you're done. So the direction of V cross B from that right hand rule is the direction of your thumb. Now you've used then the right hand rule, notice how I abbreviate it, RHR, to get the direction of V cross B. In this case, it's got to be perpendicular to the tabletop. And the right-hand rule tells, because that's the plane of V and B, the right-hand rule tells me it's vertically upward. Now that's V cross B's direction. There's still another step. You have to ask, is this particle's charge down here? Remember, it's a particle. It's got Q. Is that particle positively charged? Then the direction of the magnetic force is the same as the direction of V cross B. There it is. Or is this particle's charge, Q, a negative number? Then the direction of the magnetic force, FB, is exactly opposite to V cross B. So it'd be vertically down. It's really important to remember that last step. First you do the right-hand rule to get the direction of V cross B. And then you account for whether the Q is positive or negative. Okay. All right, let's do a little practicing together with the magnetic force. Okay, so we got a figure here. We have three situations in which a positively charged particle, that's important, positively charged particle, moves at velocity v through a uniform magnetic field B arrow and experiences a magnetic force FB arrow. They didn't actually draw the particle, which they had. I would tend to put it right where the velocity vector arrow is. So in A and B it would be like that, and in C it's behind that V arrow. Notice they also draw a magnetic force arrow in blue, a magnetic field arrow in green. And some of these arrows might be pointing out of the screen towards us or into the screen away from us. And our job in each situation, A, B, and C, is to determine whether the orientation of the vectors as they're drawn is physically possible. Okay? Is it even physically correct? And all of this boils down to proper application of F magnetic arrow equals Q times V arrow cross B arrow. Now, we know already that the Q is positive. It's a positively charged particle. That's good news. Okay? That means whatever direction I get from the right-hand rule for V cross B, that's the direction of F magnetic. Right? So V cross B and FB are in the same direction. You can see that, right? In the same direction. That's got to be true. If that's not true in the picture's wrong. Also, F magnetic must be perpendicular to both V and B. Okay? FB must be perpendicular to both V and B. So let's go through these case by case, A, B, C, and see if the picture is correct. All right, picture A. The velocity is in the plane of the screen, kind of up and to the left. That picture, that representation right there means the magnetic field, B arrow, is directly into the screen, away from us. And the resulting magnetic force on the particle, okay, which would really be drawn there, with its tail anchored on the particle, is to the left. Is that correct? Is that even possible? You can think about it. You're welcome to pause the video if you want to think about it, and then come back. Okay, did you say that this is not possible? How do I know that? Well, what did I just say right here? F magnetic must be perpendicular to both V and B. There's the F magnetic. Look at the V. Are those two perpendicular to each other? No, that's not possible. That picture is not correct. Now let's look at case B. Is that possible? Pause the video, think about it, and then come back. All right, did you say that that one could happen? Check mark. Well, because how do I know? Well, the V is up and to the left. The B is to the left. Nothing said the V and the B have to be perpendicular to each other. And then it claims the resulting F magnetic. Now that picture means that it's coming straight out of the screen towards us, like the tip of an arrow. And that would then be perpendicular to both V and B, wouldn't it? Furthermore, if you applied the right-hand rule for the V and the B, and took the fingers of your right hand and pushed the V on top of the B, your thumb would point directly out of the screen towards you. And for a positively charged particle, that would be the direction of F magnetic. So that picture completely satisfies the right-hand rule. Okay, what about picture C? The magnetic field is kind of in the plane of the screen and up and to the left. The magnetic force is in the plane of the screen and to the left. And the velocity of the particle is directly out of the screen towards us. Is that physically possible? Okay, did you say, no, not possible? How do I know that? Because F magnetic must be perpendicular to both V and B. And in this case, there's the B, and there's the F magnetic, and they are not perpendicular to each other. All right, so that cannot be true. Now let me give you another little picture here to think about. Let me give you the three coordinate axes, X, Y, and Z. And by the way, this kind of drawing, which will be pretty common in this chapter, is trying to show you 3 dimensions on a 2-dimensional surface. The way you're supposed to interpret this drawing is the plus y-axis is in the plane of the screen to the right, the plus z-axis is in the plane of the screen upward, and the plus x-axis is coming straight out of the screen towards you. And here's our particle, right there. And this particle's charge Q is a positive value. And at this instant in time, let me extend the x-axis back that way. The velocity vector of the particle is in the xy plane, v, making an angle an angle of 30 degrees like so. And the magnetic field is straight up along the z-axis. What can you tell me about the direction of F magnetic? Okay, that's what I'd like you to think about. Pause the video, think about the direction of F magnetic, and then come back. All right. Notice the angle between V and B is 90, right? V is in the xy plane, B is along Z. That's a 90-degree angle. That's okay. All right? But the magnetic force has got to be perpendicular to both the V and the B. Note that V and B form a mathematical plane. Any two vectors form a mathematical plane. the V and the B's plane, well, it intersects the XY plane along this line. And it goes straight up and down, along, parallel or along, containing the Z-axis. The magnetic force has got to be perpendicular to this plane that goes straight up and down, containing the Z-axis, and intersects the XY plane along that dashed line. Let's get the direction of that F magnetic. First, use the right-hand rule to get the direction of V cross B. Try that and see what you get. From right-hand rule. Well, I like the two-pen method. I'll have a red pen for V and a green pen for B, and I'll hold them with my left hand with a common tail. I'll then reach in, okay, with the palm of my right hand open, so as to push the red pen on top of the green pen and see which way my thumb points. And that'll be perpendicular to the plane of V and B, and my thumb points this way. That's perpendicular to that plane of V and B. Then I figure out the direction of F magnetic, because I have to account for the charge. Since the charge is positive, the direction of F magnetic is the same as the direction of V cross B. If the charge were negative, it'd be exactly opposite, back that way. All right, so practice with the right-hand rule is going to be a large chunk of this chapter, because this is the way the magnetic force on a moving electrically charged particle moves. Or behaves, I should say. All right, one more thing in this video. We need a way to visualize the magnetic field produced by a magnet. Just like we had to visualize the electric field produced by charges. And so we draw what are called magnetic field lines as a way to visualize magnetic field, okay? However it's produced. The picture here shows a good old-fashioned bar magnet, which is a chunk of probably maybe iron that's been permanently magnetized that you can then just hold in your hand. We'll have some in class. All right, so then you draw for your magnet some magnetic field lines. And this bar magnet has magnetic field lines that you see drawn in green, and they have arrows on them to represent a direction. And then at any given location in space, like right there, the actual magnetic field vector, B arrow, at that point, is tangent to the magnetic field line at that point in the direction of the magnetic field line. So that's what it would look like roughly, the B arrow at that location. At this location right here, the B arrow, it's got to be tangent, it'll be straight down. Okay, so the actual B arrow at a given point is tangent to the magnetic field line passing through that point. Like with electric field lines, the tighter the spacing of the magnetic field lines, the stronger the magnetic field. That tells me the magnetic field is quite strong inside this bar magnet and also right near the two ends. Here's something else that experiment tells us. Magnetic field lines form closed loops. They circulate around. They have no beginning or end. Right? If you look at all those carefully, they're just closed loops, even if it doesn't appear like it. Like this one right here, it actually continues around and connects there. And this one continues around and connects there. And this one continues around and connects there. We have found no situation where once we've mapped out the magnetic field, we get anything other than these loops that close on themselves. Okay? This is related to the fact, apparently, that there is no such thing as what we would call a magnetic monopole, a magnetic single charge, like there is in the electrical case. An electric monopole is just an electrically charged particle. If it's positive, the electric field lines begin on it and radiate outward. If it's negative, they come in and terminate on it. Apparently there aren't any magnetic versions of that. no magnetic monopoles. So no magnetic field lines can begin or end. They just form closed loops. With a bar magnet, the convention is to call the end of the magnet from which the field lines emerge the North Pole, N. That's right here. See? Field lines are coming out. So we call that the North Pole. And then the other end, where the magnetic field lines go in, is called the South Pole, S. Okay? Earth, for reasons we don't completely understand, produces a pretty strong magnetic field, probably from the internal rotation of the magma and core. And so it turns out that Earth, I just draw it as a kind of a spherical shape, in its rotation about its axis, produces magnetic field lines that circulate around. It's just a very minimal representation, like that. But notice that at this top part, they're going into the Earth, and this bottom part, they're going out. So if the Earth acts like a bar magnet, this top part is actually the South Pole. The bottom part is the North Pole, except everybody calls it the North Pole, don't they? Up at the top. That's unfortunate nomenclature, but it's really, in terms of a magnetic field, it's like that. Here's something we'll demonstrate in class. Like poles of two magnets repel each other, like two north poles or two south poles. And opposite poles of two magnets, a north and a south, will attract. Okay? Just think that is an empirical fact. You get other shapes of magnets besides bar magnets. Here's two common ones, the horseshoe and the sea magnet, just because of the shape of the permanent magnet, with a north pole and a south pole, and magnetic field lines coming out of the north pole and going into the south pole. And that's a simplified representation, but that's kind of basically it. Okay? And you can see that the field is pretty strong in the space between them, between the poles. And then the sea magnet, well, it's more shaped like a sea. It's got a north pole and a south pole. And you get a pretty strong uniform field right in that space between the poles. So the other shapes are also common. Okay, so the last thing for this video, class engagement on Blackboard. And it goes like this. We have three situations, snapshots, whatever you want to call them, of a charged particle moving with velocity v arrow through a uniform magnetic field B arrow. In each situation, we are to state the direction of the magnetic force on the particle, right? Magnetic force, F sub B arrow. What is the direction of that? Okay, now I will give you a little bit of help. The answers will be one of the coordinate axes directions. Plus x, that way, negative x, that way. Plus y up, negative y down. Plus z out of the screen, negative z into the screen. That's true for all the situations. You can see that some of the particles, one of the particles is positively charged, and the other two are negatively charged. And then you have a velocity vector and a magnetic field vector. So the answers are either, in each case, either plus x, plus y, plus z, minus z, or none if the magnetic force is equal to 0. And that's what you enter on Blackboard. Now there is going to be another video, but I'm going to pause on this one for now. And in the next video, we're going to look at an electrically charged particle moving in both an electric field and a magnetic field. And that'll be the next video. That's all, though, for this video.